I'm Keya Ghonasgi, and I'll be presenting our work on capturing skill state in curriculum learning for human skill acquisition. This work has been done jointly in the Renew Robotics Lab and the Learning Agents Research Group at the University of Texas at Austin, in collaboration with the Brain Learning, Animation, and Movement Lab at Johns Hopkins University. Recent work in robotics, especially in the design of exoskeleton robots like the pictured Harmony exoskeleton, has greatly expanded the world of rehabilitation training in terms of repeatability, intensity, and targeted practice. However, how best to use these devices for effective rehabilitation is still an open question. Prior research has shown that motor relearning post-neurological injury is akin to novel motor skill acquisition. Thus, understanding the mechanism behind motor learning and improving its efficiency are a key component of rehabilitation design. This motivates our high-level goals of characterizing motor learning in healthy humans, leveraging this characterization to design training for novel skill acquisition, and applying what we learn from healthy motor learning to rehabilitation. Ultimately, we want to develop a strong understanding of motor learning and consequently design training protocols to effectively and efficiently promote learning. Consider the example of serving in tennis. Most professional tennis players use an overhand serve, but anyone who has learned to play the game knows it isn't as simple as picking up the ball, throwing it in the air, and aiming. Learning involves improvement of performance through dedicated practice. However, it is difficult to characterize the learning itself. In the tennis case, learning will involve improvement in the form of coordination between the two arms, understanding the trajectory of the ball after release, timing of contact between the ball and the racket, development of upper arm muscles to increase power, and so on. Even more difficult is using this characterization or model of learning through practice to build a training protocol to learn efficiently. A coach might be able to intuitively know what a person is missing in their training and what they need to improve on, but this kind of intuition takes years of experience. Consider two cases, one where a robot is learning to manipulate an oil can, and one where a person is learning to manipulate a cup of coffee. In the case of the robot, we can implement reinforcement learning to train the robot. We can explicitly define the robot's initial policy, state space, action space, and shape the reward to the task being learned. In the human learner case, this information is impossible to get explicitly. You might explain to the person how the task must be done and describe the reward structure, but cognitive and motor variability will add noise to the way in which the task is interpreted and performed by the person. As confirmed by motor learning and control literature, we can only estimate a person's skill and learning through changes in observed performance. In this work, we will discuss a vocabulary to leverage this observed performance in characterizing learning. Knowing a person's skill level is only the first step to designing a training protocol. There is no standardized approach for designing training for novel skill acquisition, as it is difficult to know what kind of practice will result in optimal learning. Several theories in motor learning and education, such as the challenge point theory, support the use of curriculum-based training for skill acquisition. The challenge point theory introduces the concept of potential learning benefit, a measure of how much valuable information is learned when a person performs a task. For a learner at a given skill level, this potential learning benefit is expected to vary as a function of the task difficulty. The theory further states that, given the performer's current skill level, there is an optimal level of challenge called the challenge point at which the potential learning benefit is maximized. Similar theories have been discussed in game design and education, such as flow channel and zone of proximal development. All of these support the idea that as learning progresses, the task presented to the learner should change in difficulty, thus giving rise to a curriculum. Our goal is to design curriculum-based training which loosely tracks the learner's optimal challenge point. Specifically, by modulating the task difficulty presented to the learner as a function of the learner's current skill level, we expect to improve the efficiency of the training protocol. However, the selection of task difficulty and its ordering is not trivial for complex dynamic tasks with multiple axes of difficulty. We thus turn to the established framework of curriculum learning used to improve learning efficiency in reinforcement learning for artificial agents. The framework of curriculum learning is best understood through an example. Consider quick chess, where the game of chess is taught to a child, presenting them with incrementally challenging versions rather than the full complex game. Each version of the game is referred to as a source task, and through appropriate ordering of these tasks, the game can be learned in an efficient manner. This framework is similar to modifying task difficulty to match the learner's optimal challenge point and has been applied to learning in artificial agents to improve the efficiency of reinforcement learning. In the case of artificial agents, the curriculum agent can be modeled as a curriculum Markov decision process that uses the agent's current policy to select the next task for the agent to train on. Unfortunately, in the human case, the learner's policy is unknown. In fact, since humans are constantly learning and cannot unlearn motor behavior explicitly, training a curriculum agent for human learners is a significant challenge. This work focuses on these challenges and proposes a design for the Human Skill Curriculum MDP, or HCMDP for short. As mentioned earlier, characterization of motor learning is difficult and can only be estimated from changes in observed performance. We define the following terms to help formulate the Human Skill Curriculum MDP. The skill state is the human's hidden internal state of learning. The proxy state is a belief about the learner's skill state. This belief is formed through the observation of performance features, which are measurable metrics that map to learning and performance changes. Finally, the measurement of these metrics must be done in probe tasks or query attempts of the task that is being learned. Since humans do not stop learning, this query task must be incorporated into the training. The agent's policy is then replaced with the proxy skill state created using a set of performance features. Whereas a curriculum MDP training an artificial agent would use the agent's policy to select the next task, the human skill CMDP behaves like a partially observable MDP. The learner's skill state is hidden and is estimated as their proxy skill state to form the HCMDP state. Before we can proceed with using the HCMDP, however, we must define a set of performance features that provide information about the learner's skill state. We define the following vocabulary selected from motor learning and control literature that will allow us to interpret learning through observation. Confidence, referring to the learner's confidence in their ability. Accuracy, referring to how well the learner performs the task. Precision, referring to how consistent the learner's performance is. And strategy, referring to deliberate control of the learner's behavior depending on the presented task. Note that these performance features could be measured using various task-specific metrics and could also be correlated. This set of performance features is not expected to be complete or unique, but does provide a starting point to define the learner's proxy skill state. We now need to demonstrate the use of our performance features in defining the proxy skill state and furthering our goal of curriculum design through an example task. This task must be designed to satisfy the following criteria. It has to be novel enough to require learning, challenging enough to facilitate improvement through practice, but not so challenging that it cannot be learned, and easy to modulate in terms of difficulty with the goal of creating intermediate source tasks to be used in a curriculum. We created the new task domain, Reach Ninja, to enable our study of human learning. The learner's webcam is used to track their hand movement, which is displayed on screen as a red cursor. Blue and black markers are imparted an initial velocity and appear as 2D projectiles from the bottom of the screen. The player's goal is to get to a maximum score by hitting the blue markers, which return a positive score, and avoiding the black ones, which return a negative score within a fixed time frame. Pilot studies showed that a baseline version of this game was not sufficiently challenging, and we further introduced the following two interventions to increase difficulty. The display of the red cursor tracking the learner's hand was turned on for 1 second and off for 1 second. This is called partial feedback. We expect that this interaction would encourage learning of the relationship between the hand movement and the cursor on screen. Second, we introduced a magnetic field around the red cursor so blue positive markers are repelled and black negative markers are attracted. The interaction between the cursor and the markers is expected to force faster movements and increased reaction times. Finally, we combine these two interactions to create the task to be learned, hereby referred to as the target task. Revisiting our task design criteria, we see that the Reach Ninja task domain is by design easy to modulate and can offer a wide range of difficulties. We perform human subject experiments to demonstrate that the task is novel and challenging enough to facilitate the study of learning. Recall the 4 performance features we defined earlier to help characterize the learner's skill state. We defined these for the Reach Ninja task to help us characterize learning of this task. The metrics we selected are as follows. Confidence is represented by an increase in mean speed. Accuracy is represented by an increase in the final score as a percentage of the total possible score in a session. Precision is represented by the increase in number of positive targets captured compared to the total number of targets hit, indicating more controlled movements. And strategy is defined by observing the average increase in score per positive target hit, indicating selection of more valuable targets. Recall that the proxy skill state is used to inform the HCMDP state. These metrics provide the required proxy skill state of the learner. We demonstrate the validity of these metrics and show that they characterize learning through human subject experiments. A total of 10 participants performed 40 sessions of the game, where each session was 40 seconds long. The participants were randomly assigned to either the control or curriculum group. The control group practiced the same target task for all 40 sessions, while the curriculum group were trained using the following curriculum. The first 4 sessions were the same as the target task, providing a baseline estimate of the participant's skill level. The next 10 sessions are the partial feedback source task, where the magnetic field is turned off, followed by a probe session similar to the target task. The next 10 sessions are the magnetic field source task, again followed by a probe task. The final 10 training sessions are the target task, followed by 4 post-training probe tasks. First, let's look at the change in final score percentage for a representative learner from the control group. As the training progressed, the performance metric improved. A similar plot for a representative curriculum group learner shows similar change in the pre- and post-training performance, though the performance during training varies depending on the task being practiced. This bar plot compares the pre-training performance shown in orange and the post-training performance shown in blue for all participants. On average, we observed an increasing trend going from pre-training to post-training, irrespective of the training provided to the participant. Using repeated measures ANOVA, we found this result to be statistically significant in the final score percentage. We also observed that the remaining 3 metrics improved with statistical significance across all 10 participants. However, we found no significant cross-effect of the training group on the improvement from pre to post-training. Further analysis of the accuracy metric in the curriculum group showed statistically significant difference in the source task difficulty. The partial feedback intervention was found to be the easiest, followed by the magnetic field source task, followed by the target task. Recall the goal of this project that we stated in the beginning of this presentation, to characterize motor learning and to use this characterization for training design. We demonstrated the use of performance features to characterize learning and defined specific metrics for the Reach Ninja domain. We also identified learning through changes in these performance metrics. We also discussed curriculum-based training design and specifically using the curriculum learning framework used in reinforcement learning. The human skill curriculum Markov decision process is defined, and the policy of the learner is replaced by the set of performance features, now referred to as the proxy skill state. Finally, we were able to see a preliminary result on the difficulty modulation of the Reach Ninja task and the effect it had on the learner's performance, thus paving the way for our future work in curriculum design. As I conclude this presentation, I want to share another platform we have been working on to test our hypotheses and curriculum design, a virtual reality game played while wearing the Harmony exoskeleton. In this video, you see a participant playing the game within the exoskeleton on the left, and the feedback they see of the game through the VR headset on the right. My co-authors and I are excited to pursue this project in these different domains and hope that we will have success in both. If you have any questions about this work, feel free to contact me at my email address or visit our website for more information on our other work. Thank you.